In the caves of northeastern Mexico, there's a fish that's evolving to actively destroy its own eyes, not slowly losing vision over its lifespan, but deliberately programming its eyeballs to self-destruct during development. The eye forms, looks promising for a few days, then essentially detonates, and boom, eye's gone. And before you start with the, "Oh no, poor little fishy" narrative, let me stop you right there, as this is not a sad story, not even close. And by the way, said fishies not only have Voltorb eye detonations, figuratively, but also taste buds on their foreheads, and somehow our favorite blue speedy hedgehog is involved, literally. And who is this, or what is this, you ask? Well, let me introduce you to Astyanax mexicanus, also known as the Mexican tetra, and it exists in two radically different forms. A normal version with eyes, color, and an unremarkable fish lifestyle, and then a cave-dwelling version that looks like it crawled out of a Guillermo del Toro film, which is kind of fitting. It's pale, near translucent, and has a skull with empty eye sockets where its, well, eyes should be. And here's the kicker. These two quote-unquote versions are the exact same species, not even different subspecies. They can interbreed perfectly and produce fertile offspring. And get this, some of these cave populations are less than 20,000 years old, which in evolutionary terms is yesterday. So this all begs the obvious question, which is, why would a fish evolve to delete its own eyes? And to understand this, you need to understand caves. These aren't just dark places, they're in some sense an energetic black hole. The darkness means near zero photosynthesis, which in turn means near zero base food production. And so dinner could be bat guano that washes in during a storm, some bacterial mats, if you're lucky, or maybe a dead cricket, meaning every single calorie matters. Now, close your eyes, or delete them, and imagine a karst landscape in northeastern Mexico, which is riddled with sinkholes and flooded cave systems. Some caves have collapsed roofs where sunlight streams through, while others are more like sealed tombs, where day and night are as meaningless as which starter Pokemon you choose. And yes, I said that. The regular, non-cave form of Astyanax mexicanus looks again like a typical tetra. Pigmented scales, functional eyes, eats insects, algae, and crustaceans, and follows daily schedules. They school together, sleep at night, and do other fishy, not fishy, things. Very respectable fish behavior. Then you've got at least 30 different cave populations who look, well, messed up. And here's what's wild. They're not all one lineage, meaning they've convergently evolved to reach the same form, with evidence suggesting that there have been at least 5 separate invasions of these surface fish into different caves, with 2 distinct genetic lineages. And yet, somehow they all developed the same adaptations. So, convergent evolution within convergent evolution, perhaps. And like I said, these are not ancient lineages. The cave populations are believed to be less than 20,000 years old, which, for comparison, another odd cavefish, the Ozark cavefish, started to go blind 11 million years ago. So in other words, Mexican cavefish are basically speedrunning this whole cave thing. And when I say cave thing, I really mean they pretty much went full-on minimalist. Eyes deleted, color deleted, circadian rhythm deleted, social life unsubscribed, sleep cut down from 8 hours to 2, essentially rewriting every expensive biological system. And studies back this notion up, as researchers compared the metabolism of surface fish to their cave-dwelling counterparts who live in complete darkness. And what they found is that surface fish ramped up their metabolism during what their internal clock considers daytime, regardless of actual light, by the way, burning around 38% more energy than cavefish under identical conditions. So while the surface fish are essentially running their engine at a high RPM, cavefish are pretty much taking a permanent chill pill. And in an environment where food sources are a bit less reliable, so you could say, this cut is the difference between life and death. Well, at least the difference between evolutionary pressure and no pressure. But this still doesn't really directly answer the question about the eyes. But it's actually pretty simple, which is that eyes are expensive. In humans, the visual system alone accounts for huge energy demands, constantly regenerating photoreceptors in the retina and processing information. And for young developing fish, researchers calculated that the energy cost of sight is about 15% of their total metabolic budget, which from the cavefish perspective is 15% just for an organ that provides near zero survival value in complete darkness. But it's not just the eyes themselves. Blind cavefish also have a significantly smaller midbrain, which, as you might be able to guess, is the part that deals with visual processing. Which again makes sense. I mean, if you're not processing visual information, why maintain the expensive hardware to do it? Now, interestingly, in cavefish embryos, eye development actually starts normal. The lens forms, the optic cup takes shape, and all is good. But then, the lens cell commits what one might call seppuku, and it does this through something called apoptosis, triggering a cascade that eventually collapses the entire eye. And how do we figure this out? Well, scientists did a rather questionable experiment of lens transplants between fish. And what they found is that if you put a surface fish lens in a cavefish embryo, you rescue eye development. But on the flip side, if you put a cavefish lens in a surface fish embryo, the eye disintegrates, meaning the cavefish lens actively destroys what would otherwise be a normal eye. And the culprit? A few things. But one gene is largely responsible, and that is connexin 50, a gene that makes protein-forming gap junctions in the lens. Normally, these are communication channels between cells keeping everything coordinated. But in cavefish, mutations occur causing these connections to break down, and thus the lens loses integrity and collapses. And this gene is important not just in fish, but also pretty much every other animal with sight. And introducing just one mutation in this gene in mice resulted in cataracts, smaller eyes, and smaller lenses. And remember, cavefish have multiple mutations in this area, not just one. But interestingly enough, sometimes it isn't just one or the other, blind or seeing. For example, the Kabayomoro cave is a cave system that actually has karst windows, areas which let in light. So in other words, the cave is not fully dark. And because of that, there's a natural experiment going on. Can you guess what it is? Mixed population of eyed and eyeless fish living together, with the distribution being unsurprisingly based on the presence of light, where eyed fish are more common in light areas, and blind fish are more common in the darker areas. And yet, there is also a third type, an intermediate showing traits of both groups, likely a result of inheriting certain mutations of connexin 50, being a hybrid between the regular form and the cave form, with the intermediate result likely being caused by inheriting certain mutations of connexin 50, but not as many as the completely blind parent fish. Now, at this point I will say that evolution, and thus genes, rarely work in isolation, and one great example of this is our other star player here, Sonic the Hedgehog. No, literally. Which is actually a gene, and perhaps the greatest named one, period. In normal fish embryos, Sonic Hedgehog, or SHH, balances eye and forebrain development, and too much or too little can have peculiar seemingly opposite effects. For example, increase the development of one part of the body and decrease the development of the other. And in cavefish, SHH expression is cranked all the way up to a 10, flooding the developing brain and massively boosting jaw development genes and taste bud proliferation, but then also on the flip side, suppressing eye-promoting genes. And when I say that their taste buds proliferate, I really mean proliferate. You see, surface fish have taste buds inside, well, their mouths, just like any other self-respecting creature. But in the cavefish, they are scattered all over its head, which yes, means that they can taste things by headbutting them. Developmentally, cavefish start with the same taste bud numbers as surface fish, but around 5 months after hatching, the number of taste buds start to increase, and increase, and increase, with the growth not stopping until 18 months in age. And some researchers believe that it continues even after this point, pretty much developing throughout the entire lifespan of the fish. And so by the end, cavefish have not only way more taste buds, but also in areas quote-unquote strategically placed where they'll make first contact with potential food, like their entire face. And I don't know about you guys, but I live in the city, where I can't even begin to imagine how horrifying and how much I would hate to have taste buds on my forehead. I probably can never walk outside again. On top of this, genomic studies also show that some cave populations have not only more taste buds, but changed taste buds, having more activation of bitter taste receptor genes, with cavefish possessing possibly 5 to 6 times more conserved bitter taste receptor genes and even pseudogenes. Which does make sense when you're relying on eating mystery cave slime, bat guano, dead insects, and other organic material of unknown origin, meaning a good poison detection system is quite ideal. And so unsurprisingly, these omnivorous fish basically eat anything they can find, scavenging dead animals, dead plants, bacterial mats, pretty much whatever washes in. And that brings me to the point of, without eyes, how can they even find these things to begin with? And the answer to that is, there is another thing about fish that you should know, which is that every fish has a lateral line, which is a thing that is basically full of sensors, called neuromasts, that detect water pressure and movement. And like I said, all fish have this, and surface fish use this as well. But in some sense, it's more like an ancillary or backup system to their regular senses, being more important in poor visibility, like at night or in murky waters. But cavefish have basically turned this sense into their primary one. They've increased not only the sensitivity of the neuromasts themselves, but also their size, particularly around where their eyes used to be. And to call these things important is putting it lightly. As when researchers ablated or destroyed these sensors in blind fish, they became clumsy, unable to hunt, and even unable to school together, while in surface fish, it only impacted them under dark conditions. And this shift in how they process information has also made their hunting pattern dramatically different. In regular-sided fish, such as zebrafish, they will do a kind of jerky J-turn when they spot prey, thus visually lining them up, whereas cavefish perform a smooth C-bend, orienting their entire body towards the pressure waves that are being emitted, reflecting their reliance on their lateral line versus their sight. And to help with this, they've even evolved a bent skull. In other words, an asymmetrical curve on the skull, which researchers think enhances water flow to one side of the face, thus optimizing sensory input. And it clearly works, with Mexican cavefish showing an ability to detect prey at greater distances than their sighted cousins. Which, speaking of sight, this might be shocking to you, but can you think of something else where having eyes is, critically important? Well, my friends, that is sleep, as the day cycle generally regulates circadian rhythm in us surface dwellers. And surface fish are by no means an exception to this, and have been observed sleeping 8 to 10 hours per day. Very respectable. Cavefish, on the other hand, have cut this to as little as 2 hours, running at a level which would likely cause death in humans, either directly or indirectly. And the key to this, besides losing the eyes themselves, is the protein hypocretin, a neuropeptide regulating sleep and appetite. And mutations in genes related to hypocretin have essentially rewired cavefish into having a constant low-level alertness, which makes perfect sense, as in caves, food opportunities are very unpredictable. So if you snooze, you lose, literally. But interestingly, even with their dramatically altered sleep and no eyes, cavefish still have a functioning circadian clock. It's just that the system has been dramatically altered, as paradoxically, the cavefish internal clock almost acts like they're experiencing constant light, rather than darkness. But at the same time, the system isn't also driving heavy metabolic rhythms like it does in surface fish, which thus helps conserve energy. And another odd change between these two groups is how they treat their own. What I mean by that is that surface fish are aggressive, establishing dominance hierarchies through repeated fights, with these fights and aggression, which are also quite common, to say the least. On the flip side, cavefish have almost completely lost their aggressive behavior, with fights being up to 10 times less common than in the regular variety. And often, what looks like attacks are really just food-searching attempts. And the fact that starved cavefish become more quote-unquote aggressive towards their friends support this notion that they're really just desperately searching for food, not actually fighting, with the intent of establishing dominance, like what would be seen in the surface fish. And these behavior differences appear to be caused by changes in the serotonergic system, with the changes reflecting what is essentially redistribution of brain resources from social behavior to foraging, which seems to have happened in yours truly as well. And speaking of social cognition, surface fish also school intensely, like many other types of fish, and have relatively complex social hierarchies, while on the flip side, cavefish go more solo dolo. However, interestingly, hybrids between the cavefish and their light-loving relatives showed in some sense an increased schooling tendency. However, researchers think this is actually because of their near bottomless appetites, where this increased social behavior is really just because they want to cannibalize each other, as when food is scarce enough, protein just becomes protein, no matter where it originally comes from. So maybe that's the real reason why schooling behavior has fallen by the wayside in the cave variety, because I mean, who wants to be swimming around with Cannibal Jimmy? Now thankfully, the need to eat each other is perhaps slightly decreased by the fact that they've also adapted their energy storage system, making the need for such behaviors a bit less. And what I mean by this is that cavefish can actually store up to 4 times more body fat than surface fish when food is available, being kind of like preppers stockpiling for the apocalypse, except the apocalypse is just normal cave life. And speaking of normal cave life, this probably won't come as a surprise, but cavefish aren't alone, so to speak. For instance, the European olm, a pale salamander in the Dinaric Alps caves, also went blind and albino, but took a different strategy. Instead of staying active, olms slow everything down. They can live 100 plus years, survive a decade without food, and also barely move, being known to stay within the same couple of feet or meters for years. Which is freaking insane when you think about it, because I mean, can you imagine staring at the same wall with no change for years on end? Yeah. And back across the pond, the North American amblyopsid cavefish independently evolved similar traits through their similar cave home. And these examples are by no means the only ones. As in fish alone, over 200 cavefish species have been discovered that share the same pattern: lose eyes, lose pigment, and enhance other senses. And the reason for this is pretty intuitive, which is that cave environments are so constrained that evolution keeps arriving at the same solution. And this happens with such frequency that it even has a name: troglomorphy, describing the suite of traits that evolve in cave-dwelling animals, being one of the strongest cases of convergent evolution we have on the scale, and with such a host of different types of animals. So going back to the first question, why would a fish evolve to lose its eyesight, the most important sense for the vast majority of animals? And the answer is pretty clear by now, because it makes sense. Thanks for watching, and until next time.